In this example, I'll be performing a normal modes analysis and frequency response analysis on this given scenario. Full details of this exercise are on page 433 of the PDF linked in the video description below. I'll first begin by opening Patran. The units for this example are in inches, pounds, and PSI. I'll create my new database, call it problem 24. Hit OK here. Under geometry, I'll define a surface that is 12 inches down the X and 2 inches in the Y. So that would be 12, 2, and from the origin. Next, I'll mesh this using quad elements. So measure surface, select the surface, uncheck automatic calculation, give it a value of 1, and hit apply. Next, I'll define a node for my tip mass and my base mass. So here under node, edit, my first node is located at 0, 1, -1, and my second node is located at 14, 1, 0, and hit apply. To get a better view of the nodes, go to home and hit the node size, and there you have the two nodes. Going back to the meshing tab, go to element, edit, go to shape, point, and pick this node. It creates a point mass, and select this node. It creates another point mass. Let me hide the node size, and then point elements are represented with triangles. Now I have to create two bar elements here. So back in meshing element edit, you would change this to bar and simply go from any of the two nodes. So from here to here, and from here to here. After this, I want to define an RB2 element. So I will click the RB2 here under MPC. I will define my terms. I'll first start with the create independent, and I'll uncheck auto execute. I'll select this outer node and I'll hit apply to drop it in here. Next, I'll select these three nodes, and I'm holding the shift key to select multiple nodes. I'll select all the degrees of freedom and I'll hit apply to drop it in here. I'll hit cancel and hit apply. And you'll see my MPC in sort of a pink color. You can turn them off and on using the MPC markers on and off icon here. After this, I can move on to the properties tab to define my materials and properties for everything else. I'll click isotropic to define my first material. Call it matte. Under input properties, I'll give it a Young's modulus of 10e6 psi, Poisson value of 0.3, and a density of 0.026 pounds second squared per inch to the fourth. And I'll hit apply. Next, I'll assign this material to the surface. So under 2D properties, click shell. Under property name, hit shell, or type in the name as shell. Under input properties, give it a material of, use the material we just made. For a thickness, give it a thickness of 0.5 inches. Hit OK, and for your application region, select the surface. Add it, OK, and apply. Next, we want to give our bar elements some stiffness. So under 1D properties, click spring, and I'll call this K. Under input properties, our spring constant is 50 pounds per inch. Our degree of freedom is UZ. Now hit OK, and for application region, I'll select beam elements and make sure you have this selected. I'll select elements 27 and 28. The numbers may be different for you. Add it, OK, and apply. Next, I want to define our mass for here and here. So under 0D properties, select mass here, and I'll call this first one M. For options, make it lumped. For input properties, give it a mass of 0.5 pounds second squared per inch. Click OK, and for application region, we want to only pick point elements, so select this icon. Pick this point element, it's element 25 in my case, add it, OK, and apply. We'll make a next one, base M. For your input properties, give it a large value of 1e6 pounds second squared per inch. Hit OK. For your application region, select this point element, add it, OK, and apply. Now I can move on to my load and boundary conditions. For my first displacement constraint, I click this icon, and I'll call it 1, 2, 4, 5, 6. And first I'll define the input data. I'm preventing motion in the 1 and the 2 directions. And the third is blank. I'm preventing rotation about the 4, the 5, and the 6. Hit OK, and for application region, select this one node. So switch this to FEM, select this node, node 41, add it, OK, and apply. Next, I'll create a new one called 246. So I'm preventing translation in the 2. I'm preventing rotation about the 4 and the 6. Hit OK, and under application data, select these nodes. Click add, OK, and apply. Now I can go ahead and move on to my normal modes analysis. So under the analysis tab, click analyze entire model, go under solution type, and select normal modes. And let me review the solution parameters. I don't think I have to modify anything here. Hit OK here. OK. Under subcases, modify or select the default subcase. Make sure it says default here. Go to subcase parameters. We want to know the frequencies between 1 and 100. So once you do that, hit OK and click apply. Make sure it says MSC Nastran subcase create here. Click cancel. You'll notice we'll be analyzing the default subcase. Click OK here, cancel. Hit apply. Once you do that, import XDB results. Go to the results tab and you'll see that our 1, 2, and 3 frequencies are 2, 12, and 71. And when we go back here, we get 2, 12, and 71. And you can view the mode shapes as shown here. So there goes. Oh, let me clean this up. Here's mode 1, mode 2, and mode 3. Now moving on to our modal frequency response analysis. Let me go back to the boundary conditions tab and define a new load case called frequency or freq-LC. And for type, make it time dependent and hit apply. And now let me define an LBC field that is non-spatial. So click this icon, call it freq, check frequency for my input data. My first value will be 0, my next value will be 200. This value will be 1, and this value will be 1, 2. Hit OK. Hit apply at the bottom or just hit enter. And make sure it said field frequency created. A way to find out if it was created is go to home, turn on your model tree, and here under fields you'll find this field. Under the boundary conditions tab, we'll define a nodal force, call it F. Under input data, we'll give it a value of 0 in the 1, the 2, and for the third direction, give it a value of 1e6. Scroll, or make sure to close this. Scroll to the right and select this frequency and add it to the adjacent box. Hit OK. For application region, select this node, add it, OK, and apply. So you'll see it added here to the base. Before we analyze this, we are working with the frequency load case. And now if I right click and modify it, you'll see that so far there's only a force in this load case, what I have to do is add the previous displacement constraints, and I simply click them and they are added to the load case here. I hit apply here to confirm the update, and here I get the feedback: load case frequency LC modified. Minimize this. Now I can move on to my analysis. Here under analysis, analyze entire model. Call this problem 24 frequency response. Under solution type, select frequency response and make sure it says modal here. Click OK. Under subcases, we are no longer working with the default subcase. We are working with the frequency LC subcase. So select that. Make sure it's dropped in here. Under subcase parameters, define the frequencies here. So make sure it says 100 here, enter, and 200 here for the number of increments. Make sure it says 100 and 200 here. Hit OK. For modal damping, switch this to structural damping G. Click define modal damping. For frequency, it will be 0 here and a 0.4 here. Add another row. Here, type in 2000 and 0.4 here. Click OK on all these windows. Except for this one, you want to change your output request. So far, the analysis will give me displacements and SPC forces. I don't want these. So select one, delete. Select another one and delete. I want my accelerations and velocities. Hit OK at the bottom or just hit apply here. And make sure you get this update, subcase create. Click cancel. Under subcase select, if I were to hit apply and analyze this model, it would try to use the previous default load case, which only has the displacement constraints and not the load. So I have to add this new one, and I'll delete and remove this old default one. So here I have frequency load case ready to go and be analyzed. So I'll hit OK and hit apply. After that, I'll import my results. So I'll click XDB and hit apply to import. Now go to results and hit graph. Here I'll click this icon that expands all the results, and here you'll see your previous frequencies. This time you see an additional set of results going from 0 to 100. Hold the shift key and select the last result. I want to view my translational accelerations. Make sure this is magnitude, and I want to view this for the base. So node 41 in my case, the tip of the plate, and this tip mass. So let me hit apply. And if we compare this to what they got before, that is approximately what we do get. So the max would be 3.6 and the frequency ranges from 0 to 100. Now let me clean up the values so they're easy to read here. Let me go to display attributes. For the x-axis format, switch this to fixed, and the y-axis format do the same, and hit apply. And now it's easier to read. It goes from 0 to 100 and from 0 to 3.6. Now sometimes you want to view both the model and the window at the same time. What you can do is just drag it, or go to the home tab and select tile viewports. Now I can simultaneously view the graphs. If you want to save this graph for later, what you can do is go to plot options, save graph as accelerations, and hit apply. Now I can turn them off and on. So if I were to continue my review of the results and say I view one of the mode shapes, hit apply. I see my mode shape. If I want to refer back to my accelerations, I can simply check it on. I can check it off and on. I can do the same for the fringe here. I can turn it off and on. Let me expand this. I'll save it, and this concludes this example.